Hello class, so today we're going to be learning about thermodynamic versus kinetic control in chemical reactions. So let's first figure out what these long words mean. Thermodynamic can be broken down into two different words. So thermo just means heat and dynamic just means change. So when you see thermodynamic, you can just think about a change in heat or a change in temperature. So the thermodynamic product will form at high temperatures. And that means that the kinetic product will form at low temperature. So kinetic really just means motion or speed. So the kinetic product will form quickly, and the thermodynamic product will form slowly. And now I'll just mention two other things that differentiate between thermodynamic and kinetic control, and that is the intermediate, or kind of the middle product. For kinetic products, they have a more stable intermediate. And they end up with a less stable product. And this makes sense. That's what makes them fast, because the intermediate's more stable. It's easier to get through to get to the product. And on the other hand, the thermodynamic product will have a less stable intermediate and a more stable product. And this makes sense because if you have a higher temperature, that means that you have more energy and you can get through this less stable intermediate to form the better, more stable product. And that brings us to the point that nature loves stability. So nature wants everything to be as stable as possible. So when you have a chemical reaction, if you have a low temperature, it will go through the more stable or easier intermediate or middle ground to get you to the less stable product. But if you have enough temperature, you will go the preferred route, which is through the less stable intermediate, but to get you to the more stable product. But that only happens if you have enough temperature, if you have enough heat. So let's give a little example. Let's say that you get $5 a week for allowance, and you get it every Friday, and you go to the store every Saturday with your mom. And after the first week, you're going to start right here, and we'll say that on this graph here, the top is less stable, and the bottom is more stable. So the top is less happy. You're less happy if you're up here on this graph. Down here, you're more happy. And you're starting right about in the middle. So after the first week, you have $5 in your hand and you go to the store with your mom and you see two things you really want to buy. You see a $5 Hot Wheels car and you see a $25 remote control car. So you have two different options. You can buy the $5 Hot Wheels car, so let's just pretend that you go ahead and do that. So you're going to go up here, spend the $5, so you're less stable at this point because you have to spend all of your money, and then you end up over here with your Hot Wheels car. And that happened pretty quickly. That was the kinetic product because you just went up and spent your $5 and you ended up with your Hot Wheels car. And I'll show you how that looks different from the thermodynamic product. So let's say you waited 4 weeks, you waited a whole month, and you saved up $25 and you bought that remote control car. So you started at the same spot, but you went all the way up here and all the way down here. So this is the $25 you had to spend, and this is your remote control car. That's what these lines represent. So you can see that this transition state, this intermediate up here, is less stable for the thermodynamic product in orange, but you end up with a more stable product over here because you have that remote control car and you like it a lot more and you're happier. So this represents if you have enough energy, or in this case money, you can get the better product. But you have to wait longer and you have to go through more to get there. So let's try another example, but let's actually use heat this time. So let's say that you're on a mountain And the first time you go to this mountain, it is 32 degrees Fahrenheit, and this is your starting point. So we're going to use the same idea that if you're up here on this graph, then you're less stable, less happy. Down here, you're more stable, you're more happy. So at 32 degrees, that's freezing. That's the temperature that water freezes. So you're really, really cold, and all you can think about doing is going over this little hill in front of you in order to get to this cabin. And I'm going to just change the color here. So we're going to go this way. You're just going to go over this little hill to get to this cabin. So you had a little bit of a struggle, you were a little less stable when you went up that little hill, but you ended up happier because you're in this cabin and you're warm. So let's now pretend that you went to the same mountain but on a different day, and it just so happened to be 75 degrees. So it's warm and sunny, and you start at the same spot, but now this time you realize that there is a taller peak that you can climb over, and your friend tells you that there is a hidden waterfall at the end. So the same hill is here, you could take this route, and you could end up in the cabin, like before, but instead you have enough energy that you decide to go up the big peak and get to the waterfall. So here you can kind of see why nature chooses this, because when the temperature is low enough, it just simply doesn't have enough energy to choose anything else. So it goes to the kinetic product, which is less stable. But when you have a higher temperature, you have more energy, and you can get over this big hill in order to get to the better product. So let's actually talk about organic chemistry here for a minute. And you may not understand these words, but I think you can follow along. So we're going to talk about butadiene. And these squiggly lines here just represent a carbon at every bend. So there's carbon, 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 4 carbons, and then 2 double bonds. And that's called a butadiene. And a common reaction is to add hydrochloric acid to this. And what happens is a carbocation intermediate. And carbocation just means that it has a positive charge on a carbon. So there's 2 different ways this can happen, and they go back and forth in something called resonance, but we're just going to talk about them separately here so you can really see what's going on. So this carbocation is less stable. This one is more stable. And I'll explain why. So this positive charge on this carbon here is next to 2 carbons, right here, carbon 1, carbon 2. But this positive charge over here is only next to 1 carbon. So anytime there's a positive charge, nature wants it to be closer to carbons. It wants it to have more friends, and that makes it more stable. So if this reaction were to continue with this carbocation, you would end up forming the kinetic product with the chlorine right here. And that is less stable. And it's also called the 1,2 product. And if you were to continue on with this reaction, you would end up with this product. And it's more stable. And it's the thermodynamic product. And it's also called 1,4. And this is more stable here because this double bond, which is what we're looking at now, is next to 2 carbons. But this double bond is only next to 1 carbon. And that's what determines the stability of the product. So you can see in this thermodynamic example, it has a less stable carbocation, a less stable intermediate, but it forms a more stable product. So this is the one that will happen at the high temperatures, which can get it through the less stable intermediate. But if you have low temperature, it'll just go right through this more stable intermediate to the less stable product, but it's still okay. So let's see this on a graph. And this one will look a little bit different than the ones before, but you can still follow along. So up here is less stable. Down here is more stable. And we will choose kinetic first. So we have the same starting point as before. And this time we have to go through 2 transition states, or 2 hills. So no matter what, we're going to go up this first transition state. We'll just call this TS1, and we're going to form our carbocation down here. And it's lower because a carbocation is pretty stable, and we can show that here. It goes back and forth. It's relatively happy. So for the kinetic product at low temperatures, it will just go up a second transition state to the product. So we'll call this TS2, and this is the kinetic product. And if you have enough heat, you'll go the thermodynamic route, which will be the same beginning. We have to go through the same transition state 1 to get to your carbocation, but once you're here, you're going to go through a more difficult transition state to get to your better product. And that's really the difference. Is right here. You go through a less stable transition state for a more stable product. And that's what we've been talking about this whole time. And just so you know, thermodynamic is actually reversible. But kinetic product, it's not. It won't go back. So really, when you think about it, just remember that nature wants to be happy. It wants everything to be the most stable. So if you have enough energy, if you have enough heat, if you have a high enough temperature, you'll go to the thermodynamic product, which is the most stable. But if you do not, you will go to the kinetic product, which is less stable, but it's still okay.